Hello everyone, my name is Wang Wei. I'm graduated from National University of Singapore and now working in Sinopec, China. The study I want to introduce today is called a load-complementarity combined flexible clustering approach for large-scale urban energy-water nexus optimization. And today I will introduce the study on 4 main parts. Well, with the continuous development of urbanization, the energy demand for different types of buildings in urban areas has increased significantly. Sustainable urban energy system, namely UES, has already become a more environmentally friendly option to fulfill the energy demand of buildings. It has more advantages than the traditional centralized energy system. It's usually located near to the user side and integrated with local renewable energy sources. For example, like solar energy or wind energy. Besides, by recovering the heat from electricity generation, UES can further improve the energy supply efficiency and also gain more economic benefits. In addition, energy and water are recognized as two critical resources to human livelihood. The interrelation of production and consumption between energy and water are increasingly important for urban planning and management. So the energy-water nexus systems are becoming more and more important for city planners. And to solve a standalone building level UES optimization problem, the MILP, namely mixed integer linear programming, is the most commonly used one. But when the modeling scale increased to neighborhood or district level, like with dozens of buildings or even hundreds of buildings, the solving process could be quite time-consuming. A large number of integers and variables will increase the complexity of the whole problem and may even lead to the problem unsolvable. So in order to better solve the large-scale UES problem, several decomposition methods are conducted. Usually the problem scales can be decreased into smaller ones from spatial or temporal aspects. And for temporal perspective, typical days or periods are commonly selected to represent the demands of the whole year. And when the decomposition techniques are applied from spatial aspect, the large-scale district can be divided into several smaller regions, well, for example, density and distance-based clustering approach are two commonly used clustering methods. And what's more, the latest studies have proven that by leveling up the overall demand profile through accumulating multiple profiles, the complementarity effect can effectively reduce the total project cost. And to better understand the UES optimization problem, now please focus on this graph. This picture illustrates a generalized UES optimization problem in which dozens of buildings with different functions exist on a district map, and each building can build its own energy system and connect to each other by energy network. And to lower down the scale of the problem, both of the density-based and distance-based clustering technique have their own advantages and disadvantages. Well, for this density-based clustering technique, a district is clustered into several neighborhoods and allowing several outliers maintaining standalone. But when it comes to the optimization process, it is difficult to determine whether the standalone buildings should maintain alone or enrolled in certain clusters. This might lead to suboptimal results. And in contrast, the distance-based clustering will not generate outliers However, the distance-based clustering needs to predefine the number of the clusters, which is generally unknown. And moreover, a common challenge exists for both clustering techniques. That is the selection of the optimal design mode between the energy hub mode and distributed mode. For the energy hub mode, there's only one set of energy system installed at one place at the hub, serving the energy demands of a neighborhood. Whereas the distributed mode enables each building to build its own system and also connect with neighbors for energy transfer. And the study indicated that the distributed mode can achieve roughly 4% more cost savings than the energy hub mode, but it is much more complex. And in order to better solve the large-scale energy-water optimization problem, a novel clustering approach is proposed in this study. It increases the flexibility of spatial decomposition and balance the trade-off between solution accuracy and computational time, and also consider the complementarity effect at the same time to further improve the project benefits. And all these efforts are made to find the optimal solution efficiently and analyze the relation between energy and water systems in a more practical way. Here are more details about the methodology. Well, the conventional density-based clustering approach firstly divides all buildings into different clusters, and the clustering results of the whole district is defined as a basic clustering map. Then the UES problem is optimized based on the clustering map to achieve optimal solutions for all clusters. And as illustrated, the right part is the details of the proposed new steps of the novel approach, which is based on the conventional clustering approach, and more details are shown in next slides. Well, in the new flexible clustering approach, 3 index assessments with flexible clustering strategy are further added to improve the clustering and optimization results. The first one is the density index to assess the relative intensive level among all buildings of each cluster and control the changing degree of new clustering results. The second one is complementarity index. And in this study, the coefficient of variation, namely the CV value, is selected to evaluate the demand complementarity for different types of buildings. And once a basic clustering map is obtained, the density and the CV value of that cluster can be calculated. And then the UES design optimization module is further applied with both energy hub and distributed mode. And based on the basic clustering map, the flexible clustering process utilizes a feedback loop, considering the distance and demand characteristics at the same time. After defining the new density constraint, outliers can be added into certain basic clusters, and flexible clustering strategy is applied to generate new clustering maps based on the basic clustering map, and then the new maps with lower CV value than before will be selected as feasible clustering maps. And the feedback loop will be repeated after defining a new density constraint. When all feasible clustering maps are picked up, the UES optimization problem is solved under the control of the computational time evaluation, which is the third assessment index. If the solving time of any new cluster is much longer than that of the corresponding basic cluster optimization problem, for example 1.5 times, the optimization process will be stopped and connected to the next feasible clustering map. Eventually, An overall economic assessment is applied to compare the optimal solution based on the above flexible clustering maps and the final optimal solution obtained from the basic map. The corresponding clustering map will be further identified in the end. The proposed flexible clustering approach is applied to a case study of newly built business zone with 60 buildings in Shanghai, China. The district includes 3 types of buildings, namely hotel, office, and shopping mall. And the energy demand are shown here, where each type of buildings has different electricity demand profile. And for one type of building, the electricity demand profile vary with the seasons. The new flexible clustering approach is applied to optimize a future energy water nexus system. The nexus system can fulfill 5 types of demand, namely electricity, heating, cooling, water, and hydrogen. The electricity demand is fulfilled by CHP, PV panel, and imported electricity from the grid. Heating demand is satisfied by boiler and heat pump. Absorption chiller and electrical chiller can fulfill the cooling demand. The nexus system also considers the demand of condensing and circulating water for chiller, CHP, heat pump, and boiler by utilizing a rainwater harvesting system. By setting the above information as inputs to the proposed approach, the optimal system design and clustering results can be obtained. Well, the left figure shows the basic clustering map generated by conventional density-based clustering approach, where all buildings in this district are divided into 4 basic clusters, and the final optimal clustering map is shown in the right figure, where 6 outliers are added into the 3 basic clusters, and the rest outliers maintain standalone. As for the economic performance, the optimization results indicate that it can save annualized total cost of around 6% and 3% compared to the basic hub mode and distributed mode. Compared to the basic hub mode, cluster 2 achieves the most cost saving, around 7%. And the proposed flexible clustering approach could lead to different design of energy network. The comparison of network design of cluster 2 in the basic and final optimal clustering maps is illustrated here. The network connections are affected by the complementarity effect of the buildings within one cluster and the energy exchange among all buildings. When the energy transfer becomes more frequent in the cluster with higher complementarity effect, cost savings can be expected. So, in the final optimal clustering maps, more packwork is built among offices and the new joiners, namely the hotels. As for the impact of demand complementarity, the results show that the reduction of CV values indeed benefit the project cost reduction. As shown by the graph here, the lower the CV value is, the more cost saving will be. Besides, in the final optimal solution, more buildings in different types are connected with more frequent energy exchange among buildings. The details of energy transfer are analyzed by taking cluster 2 as an example, and the detailed energy transfer at 4 typical time slots are displayed here. And different colors represent the energy transfer at various time slots, and the width of each line represent the quantity of energy of the transferred energy. In figure A, the electricity transfer mainly happens at 8 p.m. and 10 p.m. when the electricity demand of offices drops, but the demand of hotels and shopping malls still at a high value. And through energy transfer, the CHP in office buildings can operate at high load conditions. The larger capacity of CHP in the hotels and shopping malls can be avoided. So it is observed that electricity from offices exposed to the shopping malls like building 14, building 18, or hotels like building 33, 31, and 22. And in contrast, the electricity transfer is less significant at 6 a.m. or 12 p.m. when all buildings demand at peak or off-peak time simultaneously. So energy systems tend to fulfill their own energy demands individually. And similar to electricity, a large amount of heating transfer of cluster 2 in winter happens at night, and during which most heating energy is transferred from offices to shopping malls or hotels. Meanwhile, heating demand of all buildings is low in the early morning, for example, like 6 a.m., and heating exchange is not frequent. And the electricity transfer with the grid is also analyzed. As illustrated, a large amount of electricity is purchased from the grid at 6 a.m., then 8 p.m. and 10 p.m. due to lower price at morning time. But at 12 p.m., although the purchasing fee is relatively high, significant amount of electricity has to be imported from the grid to meet the peak demand of all buildings. And during the evening, like 8 p.m., since hotels are still at the peak demand period, while offices demand reaches the off-peak period, the largest amount of the electricity of all day is transferred from offices to the hotels. Well, this study proposed a flexible clustering approach for large-scale energy-water nexus design and optimization problems with combined index assessments from 3 aspects, namely distance, complementarity effect, and computational time. It provides more feasible clustering maps based on the conventional density clustering approach, and further integrates the evaluation of the inner building complementarity effect and the computational cost. Such index assessment can consider the trade-off between individual and group benefits, enhance the inner energy exchange among buildings, and control the computational time to the accessible range so that lower cost and more computationally efficient optimal system designs can be achieved. Besides, by considering water usage of energy supply systems, the study could release the pressure of ensuring urban energy security and increase the sustainability of city planning and management. More comprehensive decisions can be made from water consumption aspects while choosing energy supply technologies in urban area to keep the sustainable development for both energy and water system. Well, that's all about the study, and thanks for your listening. If you have any questions, please feel free to contact me, and thanks again.